All right, so let me minimize this. Let's pick up where we left off. So this again is still assignment 2-2. We're at question number 32. Let's do it. So we're given a piecewise function that's defined as 2ax subtract 6 when x is less than or equal to 2. And the other piece is x squared plus a. That's when x is greater than 2. And it says it's a continuous function. Find the value of a if it's continuous. Well, if it's continuous, when I plug 2 in for x here, and when I plug 2 in for x here, they would give you the same answer. So I'm going to do that. Plug 2 into the top, 2 in the bottom, and now solve for a. So that is 4a subtract 6. 4 plus a, combine like terms. So I'm going to subtract a, I'm going to add 6, and then divide. And I get the answer 10/3. Number 33. Find an equation of a line through 2 points. Oh man, beginning algebra, not everything was so simple. So through 2 points, slope. So the change in y and the change in x, so we can find the slope. We don't need to simplify it down. And then the equation would be the slope, and then you'd have to take one of the points. So I'll take the first one. That's x plus 2 plus 3. Man, if it wasn't all so simple. 34. In 34, the domain. Well, we know that what's underneath the square root sign must be greater than or equal to 0. So if I got x by itself, I would subtract 3. So that's a good answer. Or you can write down from -3 to infinity, which is even prettier in some ways. But both are right. Oh, and did it say the range as well? Oh, and range. Well, for this square root function, I need to know it's increasing from this answer. So if I think of the h and the k, this will help me with the range, that 0. So the domain is that. The range goes from 0 to infinity. So we have our h and k for our square root function that helps us with the domain and range. Knowing that it's increasing helps as well. 35. Find the domain and range of this. Make sure I do both. So first thing I recognize for the domain is that, and that's a symbol for all real numbers. So all the numbers work for x, but there's one bad number in the bunch. So obviously, what's one number x cannot be? And that is -1. How about the range? How would you find the range out? Well, the range goes with the horizontal asymptote. And in this case, they are equally powerful. So how would you find the horizontal asymptote? Is power over power. So that horizontal asymptote, which is also the end behavior, is +1. So the power terms give you the horizontal asymptote, which tells you what y cannot equal. So y can equal that. So we can also write down all real numbers, but y cannot equal 1. That comes from the power terms. The domain, I look at what makes the denominator equal to 0. What makes it undefined? And the only bad value for x that make it undefined is -1. 36. So we're given a function. Cosine x subtract 1 over x. 5x. It says use a calculator. So we're going to go over to Desmos. Now, one thing I recognize for Desmos is, before I get to Desmos, is notice one is x is less than 0 and the other is x is greater than 0. That means, what happens at 0? Well, neither one of them has an equal sign part of it. So at 0, it's not defined. So here, I've already typed it in. So if I look here, here's my the piecewise I have, the top piece and bottom piece. If I follow this wave, this cosine wave, what happens at 0? Well, at 0 there is it's a hole. So at 0 there's a hole, but everything else is continuous. So where is the discontinuities? And it's when x equals 0. Now, is it removable or not? Well, does the limit exist? Look at the right and the left. Do they both approach the same answer? And the answer is yes. They both approach 0. So the limit exists, so it's removable. So at what x value is there a discontinuity? At 0, because it's undefined there. And the limit exists, so therefore it is removable. So let's come back here. So at x equals 0 is a removable discontinuity. Now, if there was a jump there, it'd still be a discontinuity, but it would be non-removable because the limit doesn't exist. But because the limit exists, it is removable. 37. Again, I'm going to use the calculator. Now, if I'm only worried about the discontinuities, I'm looking at the denominator. But I also need to know the numerator to know if it's removable or not. So, if I factor the numerator out, that's plus 2 and minus 2. So I got to keep that in mind when I type in the denominator into Desmos. So I'm going to type the denominator only into Desmos and find what are the zeros of the denominator. Those are all my discontinuities. I need the numerator to know if it's removable or not. So let's first of all, let's go back here. So I'm going to type in x cubed. What else do we have here? Subtract 2x squared. Subtract 2x plus 4. So I'm just really looking here at these values here that make it 0. So what x values make the answer 0? So at x equals positive and negative 1.414, there are non-removable discontinuities. And then the other one, instead of positive and negative 1.414, is 2. Well, I'm going to come back here and recognize that that 0 matches a 0 on top. So positive 2 is also a 0 on top. So you have a 0 over 0. It's removable. And because it's removable at x equals 2, there's a removable discontinuity. So we could remove the 2 and then plug in 2 after you remove it to get an answer. So the limit exists at 2, but does not exist here. These are non-removable. 38. 38 says, is there a c value between negative 2 and 2 for f at c equals negative 1 for this function, x squared minus x over x? And if there is, find the c value. If not, explain why not. So first of all, it has to meet two conditions. So the first thing I'm going to do is this for 38. I'm going to factor the numerator. So I want you to notice that there is a discontinuity So there is a discontinuity right here. And I know it's removable, but it's still discontinuity. That just means it's a removable discontinuity. And what is that x value? What makes that 0 on the bottom? And it's when x equals 0. So at x equals 0 is a removable discontinuity. Now, for this to work, that is the intermediate value theorem, two conditions have to be met. One is it continuous? Well, it's not continuous at 0. Is 0 somewhere in my interval? So from negative 2 to positive 2, is 0 inside that? Yes. Therefore what? There is no c value. Because it is not, and here's a great word, continuous at x equals 0. So there are two conditions. One is continuity, and the other one would be if you plug in negative 2 and positive 2, that -1 is in between those two y coordinates. But it failed the first condition, so it's over. So for 38, does the intermediate value theorem guarantee a c value? And the answer is no. And why doesn't it? Because at 0, there's a discontinuity, and it's in the middle of my interval. Done. 39. All right, 39 is off the graph. So I'm going to write these down, but then I'm going to have the graph to be able to answer it. So all these is just looking off the graph and knowing what you're looking for when you look off the graph. So let's look here, and then I'll put the answers on the other sheet. So what's the answer for the limit as x approaches 6 looking at this graph? So I see where 6 is. So as I approach from the right and left, do they agree what the limit is? Now there is a hole there, but that means the limit can still exist if they approach the same y coordinate. So from the right and left, they both are approaching 2, and that's the answer. For number 40, look off the graph. Can you find a limit off the graph? So all I want is as x approaches 4 from the right. So identify 4 from the right. So if I look here, from the left we have one answer, but then there's a jump. And then from the left we have a different answer. So from the right and from the left. Now the question asks, well, 41 asks the other question. But 40 first asks from the right. So from the right, what's the y coordinate it's approaching? So the answer is 1. And then from the left, what's the coordinate that it's approaching? So from the left, the y value is 3. So that's what I'm looking for. So at 40, the answer is 1. And for 41, it's approaching 3. 42. Off a graph, can you evaluate a limit? So as x approaches 4, so here we are, back here. Now, does left agree with right? So there's a one-sided limit here, but because of the jump, the two-sided limit does not exist. 43, off the graph. The limit of the function as x approaches 3. So here I am at 3. From the right and from the left, does it agree what the y coordinate is? It's 2. Notice we have a value up here, but that's not the limit. So the function value is way up here, but the limit is what the y coordinate is as it's approaching. So the whole is okay. What's the y coordinate? It's approaching from the left and right, and the answer is 2, even though the function value is up here at 3. So the limit value is 2. Now, it's not a continuous function, but the limit still exists if it's not continuous. 44. So off the graph for 44, the limit as x approaches 1. So here we are at 1. From the right and from the left, what does it approach? And you can see it approaches, both sides approach 1. So we're looking for that y coordinate that it's approaching and seeing if it agrees from both directions. And then 45 to 48 says look off the graph and tell me if it's continuous at these things. So at x equals 1, and I'm looking for holes, jumps, and asymptotes. So at 1, is it continuous? So look at it. There's no holes, jumps, or nothing. There is a nice little corner here, but that is continuous at 1. I don't see a hole, I don't see a jump, or an asymptote. So at 1, yes, it is continuous. For 46, is it continuous at x equals 3? So at 3, I see a hole. That hole tells me that not continuous. So the answer is no. 47. Is it continuous with those x values? So at 4, what happens at 4? I see a jump, not continuous. 48. When x equals 6, what happens at 6? There's a hole at 6, not continuous. So the only x value where there's continuity was when x equals 1 for those examples. And so that's why it was yes. All the others had a reason. 46 and 48, there were holes. And then 49, there was a jump. Or 48. All right, 49. We're almost done. Find all the discontinuities without using a calculator for each one here. So let's finish with some continuity work. So f of x equals x over, now I'm going to factor this right away, x plus 2, x subtract 2. To find the discontinuities, all you have to do is look at the denominator when it's a rational function. So just the denominator. So at x equals positive and negative 2, we have discontinuities, right? Because both numbers make the bottom 0. Can you remove them? Nope. So the limit doesn't exist. These are non-removable. Number 50. F at x equals x minus 2. Now again, the denominator is factorable. So I'm going to factor it. X plus 2, x minus 2. A difference of squares. So look again carefully at x, and I'm going to separate these for a reason. So negative 2 is one answer. Now, is there anything that removes that factor to that? It's not a whole, is it? So at negative 2, it isn't removable. So this is a non-removable discontinuity. The other one at x equals positive 2 is different. So here we get positive 2. Notice the numerator, that does remove. At positive 2, there's a hole. The limit exists, but it's still discontinuity. So we say that is a removable discontinuity. 51. Oh, my favorite, the step function. 2x. So, the step function at 2x, if I look at it, what makes that an integer? So I want you to notice that not only does, when you plug in 1, 2, 3, and 4, if you plug in half numbers, it would also make it an integer. So 1 half, 3 halves, 4 halves. So every half multiple, there is a non-removable because the limit does not exist because there's a jump discontinuity for 51. Last one, number 52. 52 is looking off a graph. Where are the discontinuities and are they removable or not? So at x equals, so let's look off a graph. I'm looking for holes, jumps, and asymptotes. So let's go left to right. So the first thing I see is when x equals negative 3. I see a hole, and I see the limit exists. So because of that, at x equals negative 3, there is a removable discontinuity. Let's keep going across left to right. I see an asymptote. So there's an asymptote at x equals negative 1. An asymptote is non-removable. Let's keep going left to right. So even though you could say the limit exists because they both go up, automatically an asymptote means it's non-removable. It stayed in the denominator. Keep going left to right. The next one I see, the whole, is when x equals 1. Does the limit exist? Yes. So it's removable. And then keep going. Is there any other discontinuities to the right? I see one more. That's when x equals 2. Does the limit exist there? Well, from the right and from the left, there's a jump. The limit doesn't exist there. So at x equals 2 is a non-removable discontinuity. Done. All right, Mr. G Math over and out. I'm so proud of you that you're doing your work. And until next time.